Okay, this topic, it's amines and amides that we're going to look at. So these are two more types of organic compounds. They both contain nitrogen atoms, and some of them are very closely linked to the benzene rings that we just looked at in the last session. So we're going to look at amines and amides. So amines. Amines are an organic derivative of ammonia. So if one or more of the hydrogens in ammonia is replaced with an organic group, you get an amine. If one hydrogen is replaced with an organic group, you get a primary amine. If two are replaced, you get a secondary amine. And then if three are replaced, you get a tertiary amine. The lone pair of electrons on the nitrogen atom in a tertiary amine can also bond with a fourth organic group, and this gives you a quaternary ammonium ion here. So again, I'm just going to go through this really quickly again for you. But basically, an amine is a derivative of ammonia, and we get an amine when one or more of the hydrogens in ammonia are replaced with an organic group. And as you can see, you replace one, you get a primary amine. You replace two hydrogens, you get a secondary amine. Three, you get a tertiary amine. And then quaternary amines, as I said, that's when that lone pair of electrons on the nitrogen atom on your tertiary amine also bond with a fourth organic group, and this gives you a quaternary ammonium ion because now your nitrogen is positively charged. You can also get aromatic amines, so for example phenylamine, which is also a primary amine, and we looked a bit at those aromatic amines. As you can see, that's got that benzene ring in there, so it's an aromatic compound, then with the amine group added onto it as well. So that is an aromatic amine as well. So we're going to look at quaternary ammonium salts, and we can use them as a cationic surfactant. So because quaternary ammonium ions are positively charged, so quaternary ammonium ions, so those quaternary ones, they always are positively charged. They will hang around with any negative ions that are nearby. They're going to be attracted to those negative ions nearby. The complex that is then formed when that happens is called a quaternary ammonium salts. An example of that is tetramethyl ammonium chloride. So one example of a quaternary ammonium salt would be tetramethyl ammonium chloride. CH3, 4, N plus Cl minus. So quaternary ammonium salts with at least one hydrocarbon tail, as you can see in this example at the bottom, can be used as a cationic surfactant. And what this does is our hydrocarbon tail is going to bind to non-polar substances. So this can bind to non-polar substances, and they can be things such as grease. Whilst the cationic head, so this head is cationic, and that is able to dissolve in water. So they are used in things like fabric cleaners and hair products. So we've got things like fabric cleaners and hair products. So what that means is the non-polar substances, so the grease on things like your clothes, on food, in your hair, that hydrocarbon chain attaches to them, And then the cationic head is able to dissolve in water, and we can use it in those ways to clean products. In addition, the positively charged part, so that ammonium ion at the top, is able to bind to negatively charged surfaces such as hair and fiber. So this positively charged section here is able to bind to negatively charged surfaces such as hair and fiber. And what this does is that gets rid of static. So we often use it in fabric conditioners as well. The amines. Amines have a lone pair of electrons. What amines do is they act as a weak base. And they do this because they are able to accept protons. And that is because there is a lone pair of electrons, as you can see on here, on the nitrogen atom, and that can form a dative covalent bond, which means a coordinated bond with the hydrogen ion here. So we get this dative covalent bond forming. The strength of the base depends on how available the nitrogen's lone pair is. So the strength of the base can change. So we've got the strength of the base, and that depends on how available that lone pair is. So the more available the lone pair is, the more likely the amine is to accept a proton, and the stronger the base it will be. How is a lone pair of electrons more available? Well, it will be more available if electron density is higher. So availability increases as electron density increases. And what we can also look at is primary aliphatic amines, and these are stronger bases in ammonia, which is a stronger base than aromatic amines. I'm going to look at that now. So amines have got that lone pair of electrons, allows them to act as a weak base because they can accept protons. The strength of the base depends on how available that lone pair of electrons is, and that availability works on the basis that it's more available as electron density increases. And the more available the lone pair is, the more likely the amine is to accept a proton, and therefore the base will be stronger. So primary aliphatic amines are stronger bases than ammonia, which is a stronger base than aromatic amines. So this is that idea. So the more available the lone pair of electrons is, the stronger the base. So the greater availability of the lone pair of electrons. So if we look at the primary aromatic amine, so we'll use phenylamine as an example. Our benzene ring here draws electrons towards itself, and the nitrogen lone pair gets partially delocalized onto the ring. So actually in this situation, the electron density of the nitrogen decreases, and so the lone pair is a lot less available. If we look at ammonia in the middle, we've got that lone pair fully available. And then if we look at primary aliphatic amines here, the alkyl group gently actually pushes electrons on to the attached groups. So actually the electron density of the nitrogen atom increases, and this then will make the lone pair more available. The lone pair of electrons also means that amines are nucleophiles. So it's really important to note that amines are nucleophiles. They react with halogenoalkanes in nucleophilic substitution reactions. And they're all things that we've looked at before in the past. But we're going to cover again now. Or they can also react with acyl chlorides and acid anhydrides in nucleophilic addition eliminations. So we're going to look at those as well. So they can react with acyl chlorides and acid anhydrides. And these ones would be in nucleophilic addition elimination reactions. So aliphatic amines. So there's two ways we can produce aliphatic amines. We can either make them from halogenoalkanes or by reducing nitriles. The process for producing aromatic amines is different, so we'll look at that in a moment. So what are the different ways that we can make them? So if we're making them using halogenoalkanes, and this is what we're going to look at here, if we're making them using halogenoalkanes, what that's going to be, as we just said a moment ago when we looked here, we're going to react them with halogenoalkanes with that nucleophilic substitution reactions. So amines can be made by heating halogenoalkanes with excess ammonia. So again, we're heating halogenoalkanes with an excess of ammonia. Again, words like excess are really important. And again, we heat them. And that is a way we can make aliphatic amines. So here's an example. Ethylamine can be made by reacting ammonia with bromoethane. So here we've got ammonia and we've got our halogenoalkane here. So our ammonia, remember the nitrogen's got that lone pair of electrons. The ammonia is going to come along and attack the carbon in the halogenoalkane because that carbon is going to be slightly positively charged. That happens, and because of that, the bond between the carbon and the bromine breaks, and the halogen is released as an ion. So then we get that alkyl ammonium salt being made here. And so our halogen's been released. We've had that bonding of the ammonia onto a halogenoalkane. So we've got an alkyl ammonium salt being formed with a halogen that's now been released. Then what happens is we can then go into a reversible reaction. So our alkyl ammonium salt can then become a primary amine and ammonium salt. So what happens is a second ammonia, and this is why this reaction has to take place in excess of ammonia, a second ammonia molecule donates its lone pair of electrons that are on the nitrogen to a hydrogen that's on the molecule, and that hydrogen is going to break off from the alkyl ammonium salt. So that lone pair is donated to hydrogen, the hydrogen breaks off, that bond's broken, and so then we get our primary amine here and our ammonium salt there. And that is a reversible reaction. If you make, I'm just going to check what I've got this. Okay. So if you make amines using this method, you will end up with a mixture of primary, secondary, and tertiary amines. So you're going to get a mixture of primary, secondary, and tertiary amines if you use this method. And quaternary salts, quaternary ammonium salts as well. So I'm just going to put quaternary ammonium salts, A salts. And that's because the primary amine that you produce first, as you can see here, has that lone pair of electrons. It's a nucleophile, okay? So as we said, it can act as a nucleophile. And so because that primary amine that we make first is a nucleophile, it can then react with any remaining halogenoalkane that's in the solution, and it can react with that going through a nucleophilic substitution reaction. And as long as there's some of the halogenoalkane around, further substitutions can keep taking place, and they will keep happening until you get to a quaternary ammonium salt. And that can't react any further as it has no lone pair. So if we look at that again, we make this primary amine here, which is from here. So we make that primary amine, which is a nucleophile. So we've got our primary amine here, nucleophile, and we've got our ammonium salt. That primary amine, if we still have any halogenoalkane present, the primary amine can react with that halogenoalkane going through a nucleophilic substitution reaction. So I'm just going to highlight that this is a nucleophilic substitution reaction. Going through a nucleophilic substitution reaction. And as long as there's some of the halogenoalkane around, further substitutions can take place. So then our secondary amine reacts with the halogenoalkane. Our tertiary amine does exactly the same thing all the way up until we get a quaternary ammonium ion, that quaternary ammonium salt, and they can't react any further because they do not have any lone pairs. So no further reaction because there is no lone pair. This mechanism is really similar to the reaction of ammonia with a halogenoalkane. Two amine molecules react with the halogenoalkane in succession to form a more substituted amine. For example, a primary amine forms a secondary amine, an ammonium salt with a similar structure to the original amine. So here is that as an example. So two amine molecules are going to react with the halogenoalkane in succession to form a more substituted amine. So primary amine forms secondary amine and an ammonium salt. So there's our ammonium salt here. That's our secondary amine here. And it has a very similar structure to that initial amine. So that's one way we can make aliphatic amines, is from halogenoalkanes, and that is by heating halogenoalkanes with ammonia. The other way we can make them is reducing a nitrile. So we can make them by reducing a nitrile. So you can reduce a nitrile to a primary amine by a number of different methods. This is the first method that we're going to look at. So we can use lithium aluminium hydride, and lithium aluminium hydride, this is it here. I'm just going to write that out. That is lithium aluminium hydride. And this is a strong reducing agent. So I'm just going to pop that on as well. So that's a strong reducing agent. In a non-aqueous solution. And so that's important that we've got this in here. It's in a non-aqueous solution. So for example, like we said before, dry ether, followed by some dilute acid. So here we've got our nitrile. And we are going to reduce it to a primary amine by using that lithium aluminium hydride because it's a strong reducing agent with that dilute acid, and we're going to form that primary amine. Remember that this just means reducing agent. Our H in the brackets means reducing agent. So here it is that lithium aluminium hydride that we've got up at the top. So that 4 lots of that just means that lithium aluminium hydride. Our second way of doing this, well, we have a second way because lithium aluminium hydride is too expensive for industrial use. So I'm going to just pop on here that it is expensive for industrial use. fine if you're doing it in the lab, doing small experiments, but if you use it in industry, it's too expensive. So in industry, we reduce nitriles using hydrogen gas with a metal catalyst. So we might use, for example, this we've got nickel, but it can be nickel or platinum. Could be something else as well, but they're the ones that we use platinum most often. We do this at a high temperature and a high pressure, so that's important to remember. So it's done at a high temp and high pressure. And we call this catalytic hydrogenation. I'm just going to pop the name for it above. So again, we've got our nitrile reacting it with the hydrogen gas. We've got our metal catalyst, our high temperature and pressure, and we produce that primary amine. The final type of amine we're going to look at is aromatic amines. We can make aromatic amines by reducing a nitro compound. So aromatic amines are produced by reducing a nitro compound. It could be, for example, we could use nitrobenzene. And there are two steps to this method. So first of all, we need to heat, I'm going to underline that because that's important. We need to heat a mixture of nitro compound, whatever our nitro compound is. So it could be nitrobenzene. Heat our mix of mixtures, which are heat our mixture, nitro compound, tin metal, and concentrated hydrochloric acid. Under reflux, and that's really important that this is done under reflux. So for example, if you use nitrobenzene, the salt that we form in this situation is C6H5NH3 plus Cl minus. Then, to turn the salt into the aromatic amine, we have to add an alkali. So to get the salt into an amine, we have to add, well, it's an aromatic amine, so let's add that on. Aromatic amine, we have to add an alkali, such as sodium hydroxide solution. So here we've got it in the image. We've got our nitrobenzene. We do it, we add tin, concentrated hydrochloric acid under reflux. Then once we've got that salt, so this would be an example of the salt if we were using nitrobenzene, we add sodium hydroxide solution, and then we get our aromatic amine being produced. So for example, phenylamine. They're useful compounds in organic synthesis, and they're used as the starting molecules for lots of dyes and pharmaceuticals. And finally, a tiny bit about amides. Amides are carboxylic acid derivatives. So they contain the functional group CONH2. And what that does is this carbonyl group pulls electrons away from the NH2 group. So amides behave very differently from amines. So one of the hydrogens is replaced with an alkyl group in this situation. So what we're going to do now is just go through a couple of exam questions that look at amines and amides. So the first question, you're asked to explain how methylamine, and you're given the formula, can act as a base. So what you've just learned is that it can act as a base because amines are able to accept protons, so H plus ions, or you could say it can donate a lone pair of electrons. Now get you the 1 mark. Second question, still focus on methylamine. So methylamine is a stronger base than ammonia. However, phenylamine is a weaker base than ammonia. Explain these differences in base strength. Okay, so methylamine, let's start with that. So methylamine is a stronger base than ammonia. Because stronger base than ammonia because the methyl group what the methyl group does is that pushes those electrons onto the nitrogen, increases electron density. So the methyl group pushes the electrons onto the nitrogen, increasing electron density, making the lone pair more available. That will get you 1 mark because you've answered the first part of the question. Methylamine is stronger base than ammonia. Explain why. We've done that. Now we need to explain why phenylamine is a weaker base than ammonia. Again, you need to make it really clear which molecule we're talking about. So now I'm going to say phenylamine is weaker than ammonia because the lone pair is less available. Now you need to explain why. Just saying it's less available isn't good enough. Like the top one, we explained why it's less available, more available. This time you say why. It's less available, and that's because the nitrogen's electron density is decreased because it is partially delocalized around the benzene ring. And then that would get you another mark. So then in total, that is your 2 marks. So overview again, methylamine is a stronger base than ammonia because the methyl group pushes electrons onto the nitrogen, increasing electron density, making the lone pair more available. Phenylamine is weaker than ammonia because the lone pair is less available. And that's because the nitrogen's electron density is decreased because it's partially delocalized around the benzene ring. The second question, propylamine can be synthesized from bromopropane. Suggest a disadvantage of this synthesis route. Well, as we've said, when we do this process, if we're using things such as bromopropane, we would get a mixture of primary, secondary, tertiary amines and quaternary ammonium salts. So that will get you the 1 mark. Part B, propylamine can also be synthesized from propanenitrile. Suggests suitable reagents for its preparation in a lab. So remember, that's when we need that lithium aluminium. So we need that LiAlH4 and that non-aqueous solvent, such as dry ether. Followed by that dilute acid. Why is this method not suitable for industrial use? That's because it's too expensive. So what reagents and conditions are used in industry? We use instead hydrogen gas, which will get you 1 mark. And we use a metal catalyst such as tin or platinum. No, not tin, sorry, such as nickel or platinum. A high temperature and high pressure. Final part of this question. Ethylamine can react with bromoethane to form a compound of a molecule with molecular formula C4H11N. Write an equation and outline a mechanism for this reaction. So I'm going to write this equation out first. So I'm going to write out ethylamine. The ethylamine would be 2CH3 CH2 NH2, and bromoethane would be CH3 CH2 Br. Then we're going to form the molecule of CH3. Oh, no, I put my bracket in the wrong place. Let's undo that. CH3, CH2, twice NH. That's our CH4, H11, N. And then obviously our salt at the end. So we've got CH3, CH2, NH3Br. So our mechanism, let's draw this out then. Let's do this in a different colour so it's, oops, so it's clear. So we've got H3CH2. Right, let's start this again because I throw myself off. The drawing a bit strange. Okay. Remember, draw those line pairs on. Remember curly arrows. So that lone pair is going to react with that carbon here. And then that bromine and that carbon is going to break there. So then what will form is this. Nitrogen is now going to have a positive charge. Hydrogen off both nitrogens, and then CH2, CH3. Then what will happen oops, is let's get that product drawn up, that intermediary drawn up. Nitrogen positive charge. Oh, make sure you again include them in lone pairs. I've just had to draw my eye on a different colour because I just forgot to draw them on. I'm going to react to the hydrogen, then the hydrogen, going to react, push that nitrogen away. So then we get this for me. Plus, I'm just going to write out of the product down here because it's easier. That is amines and amides. And the next session for chemistry, we'll be looking at polymers.